Anyways, so today we are going to talk about two very colorful topics. Now, it's of course not true, but they can be used in order to produce very interesting color effects, namely on one hand surface plasmons, and on the other hand the transfer matrix method. So first we are going to talk about surface plasmons, and well, the word plasmon came already up in the first lecture that we had together, so the second lecture overall. Namely, we did talk about what bulk plasmons are. So we talked about what happens when light interacts with metals. So we talked about how there will be an interaction between the light and the free electrons in the metal, and that will then lead to this dispersion relation. And the way you can understand or explain this dispersion relation is, well, dispersion relation always means that you want to know what is the frequency depending on the wave vector. And so the reason why we now have like no possibility for light to propagate in a frequency regime between 0 and the plasma frequency, the reason for this is that when light has a fairly low frequency, so below the plasma frequency, it will be able to interact with the electrons from the free electron gas, and the electrons will follow the motion of the light. And because of that, then what will happen is that the light cannot propagate into the metal, but instead there will be then dipole radiation out of the metal again, and the light will be perfectly reflected and no propagation will be allowed within the metal. So that's the case between 0 and the plasma frequency here. Notice that here the frequency is given by omega divided by omega p, so frequency divided by plasma frequency. So here at 1 is where we have the plasma frequency. So this is what happens here in this frequency regime. So no propagation of light is possible. But then if we get to a higher frequency regime, you can think about it similar to in a classical system. Like, for example, if you have your pendulum and you swing, you activate your pendulum, and if you're like going really slowly, your pendulum can follow, right? It follows in phase. Eventually, if you go even faster, you will get into this mode where they are completely out of phase. You're in resonance condition. And then if you like excite even faster, at one point, the bottom part, or like your pendulum, won't be able to follow anymore. And that is the point now that we are reaching when we are going to even higher frequencies here. We're going to a situation where our free electron gas can no longer follow, and therefore there is almost no interaction of the light within the medium anymore, and it can propagate through the medium. And in fact, if we get really, really fast, we will even approach what we call the light line. So the situation that we have in vacuum, if there's no interaction with our electrons in the material possible, then the light will propagate without any disturbance or without any interaction. And therefore, eventually it will approach the situation that we have in vacuum. And that is the case for all materials, that if we go beyond this resonance frequency, that eventually we will then approach these vacuum conditions. Okay, that's a little bit of repetition. We will today learn that this is not the full picture, but quick note on how we derive these properties. Well, we looked into what conductive materials are like. We looked into the Drude model, and so the Drude model tells us, it's this semi-classical model that tells us that we have electrons in our material, and these electrons are free to move. And an electric field, what that will do is it will accelerate an electron and accelerate it until it will have some sort of scattering event. And we call then this time from a start of an acceleration to the first scattering event. We call this the relaxation time tau. And after this relaxation time, there will be a scattering event that will bring the velocity of the electron back to 0. And then the electric field has to basically start again. So we will have, in this model, basically we have our electrons that are accelerated by the electric field, have a scattering event, and therefore their momentum gets lost, and then this continues. And so we use this model and say, well, now instead of having, for example, some sort of constant electric field driving our electrons, we have now an electromagnetic wave, so an oscillation. And therefore, we have to set up our equation of motion, which we did in the first lecture that we had together. In our equation of motion, we said we have this free electron, or first we set it up for a Lorentz oscillator, in fact, where we had a restoring force from the nucleus. But now we said for the for a metal, we do not have this restoring force anymore. So now our equation of motion no longer looks like a harmonic oscillator equation, but the restoring force is out. And we have all the other components are still left. So we still have this damping and scattering time, and we still have the exciting force, which is the electromagnetic field. And from there, then we were able to derive the epsilon in our material, which depends on omega. And so we then arrived at an equation for our epsilon, and that is a complex function. And so it's possible then to split this up into a real epsilon and an imaginary part. And together then these form the full optical response of the metal. Okay, so and the other thing is that, of course, we introduced the plasma frequency. So this frequency at which then, or below this frequency, no propagation through the metal is allowed. And above this frequency, propagation through the metal is allowed. And then we looked a little bit at real metals and how close they come to this theoretical derivation. So, for example, silver and gold. And here in the top, you have the real part and the imaginary epsilon of gold. And you can see how it follows this theoretical prediction quite nicely until a certain energy. You can also see this here, and this certain energy corresponds roughly to the yellow regime. And what's happening there is that we are no longer in this free electron regime where, to remind you a little bit of your solid state knowledge, where we have these interact, or where the electrons are just moving within one band. But what's actually happening is that electrons can now also move up into a different band. We have what we call a so-called interband transition. So going from one energy level in a certain band into another, instead of just moving around in the same band, which we are assuming for the Jodo model. And this is why we here then get this deviation from the perfect, or from the theoretical behavior that we would expect. And that's why gold looks a little bit yellowish. So this is how we can understand the appearance and also the properties, physical properties of gold. And for silver, as shown here in the bottom, silver is very similar to a perfect metal. However, there are also things here happening around 4 electron volts, where silver also does have some losses and some absorption, where it deviates from the perfect metal behavior that we would want according to our model. And that, I can tell you, I would very much also often like in my research to have a perfect metal, but that doesn't exist, and silver is the closest that we can find. Okay, and I already mentioned, okay, this gives us then the dispersion relation. And so, And so now this dispersion relation is not the full picture of what we can get if we are dealing with metals. So far we have only thought about, okay, how can light propagate through a metal, so through the bulk of a metal. However, there are also certain things that can happen at the surface of a metal, or to be more precise, at the interface of a metal and a dielectric, or to even be more precise, at the interface of between a material with negative real epsilon and positive real epsilon. So that's a very formal definition of where surface plasmons can occur, or where we define that we have an interface between, or how we define that we have an interface between a metal and a dielectric, because now you have seen that all these material properties actually strongly depend on the frequency of the light that we are looking at. So some materials might behave like metal in a certain frequency regime and like vacuum in another frequency regime. So we always need to make sure that we are looking at the right frequency regime here. On a side note, I also received a question which I addressed last week, where it was about the negative refractive index materials and how their properties are not frequency dependent. Well, again, these materials only exist in a certain frequency regime and do not exist in another frequency regime. So be very careful about this. Just because something, or let's say a material or some metamaterial might have certain properties, these properties will only be true for a certain wavelength regime. And you can very easily, for example, think about your cell phone antenna that you that is in your cell phone. I don't know if you've ever opened your cell phone and seen how complex of a metal shape you can see, or also your radio antenna. And these act as like resonant features for like much longer wavelength light, but of course with the visible light that we can see this material just as a piece of wire, and it doesn't have any particular resonant optical effects from our point of view. So always make sure that you think about what wavelength regime you're actually dealing with. But this was now only a side note. I got a little bit sidetracked here from our actual topic, which is surface plasmons. Okay, so again, we have the bulk response of our metal, and now we're looking at the surface response of our metal. So we can get a situation where we have a metal here, so that's shown here in gray. And in this metal, there are free electrons. And then we have here on our surface a wave traveling, which is a hybrid of an electron oscillation in the metal and an electromagnetic wave oscillation here in our vacuum or dielectric. And so this wave now can propagate in along the surface. And the other interesting feature about this wave is that the field decreases exponentially both into the metal, so that's what you can see here, as well as into the vacuum. So it's really a very localized situation here, where this surface plasmon really only exists at the surface. So if we go into the metal, it will disappear. And if we go into our dielectric or the vacuum, it will also disappear. So it's really localized here to the surface. And we can then define something which we call the surface plasmon polariton. And the surface plasmon polariton is now the quasi-particle describing this type of propagation of light, which is a combination of the electron oscillation and the electromagnetic field. So the same as we are saying, okay, if we have an electromagnetic wave, we call the particles that belong to this electromagnetic wave, we call it the photons. Then if you think about your solid state physics class, we have the oscillations of or vibrations of the lattice in a material, and we call the quasi-particles, so the energy bundles that correspond to this oscillation, we call it the phonons. And now you're learning about another quasi-particle, which is the particle of this collective oscillation of the electron wave here and the electromagnetic wave. And that's what we call the surface plasmon polariton. And now I got the question, are both these fields evanescent fields? And the answer is yes. So they are both the field here in the metal as well as in the dielectric they're decreasing exponentially, and thereby they are evanescent fields. They are not propagating into free space or not propagating away from the surface. So correct. Okay. These oscillations can either be excited by electron bombardment or also excited by light. We'll talk about later how we would actually excite these oscillations. So are they also evanescent along the x direction? So that is an excellent question. For now, so the answer to this question is no. They are not evanescent along the x direction because they can propagate along the x direction. It turns out, though, and that's something that we will look at in 2 slides, that this propagation here in x direction can potentially be quite slow. We'll see this in when we look at the dispersion relation, and therefore there can be a lot of absorption happening here, which might make it that they cannot propagate very far, but technically they are not evanescent. So they might get absorbed very easily or very far and might not propagate very far, but they're not evanescent along the x direction. They can propagate, and therefore they are not evanescent into that direction. I see another question, so I'm just waiting a couple of seconds. Okay, so the question is, you mentioned that we get this phenomenon at the interface with the dielectric. How did it differ at the interface with vacuum, or do we count that as dielectric too? It's again an excellent question, and it will be answered in a couple slides. So just be a little patient and we'll get there. Okay, so for the derivation, we are actually not going into the full derivation today in the lecture. However, I will briefly explain to you how you would do the derivation if you wanted to do it. So, of course, we would start with the wave equation. And what we would then have to do is we would have to separately solve the wave equation, both in the dielectric and in the metal. And then we would have to find or like match these solutions by finding the right boundary conditions. So by now defining that we have this boundary between the metal and the dielectric. And the derivation is shown in detail in Stefan Meyer's book on plasmonics, which I'm referencing also on the Canvas side. I think it's also shown in the book of, in the Fundamental of Photonics book. I am referencing this Stefan Meyer book here a lot when it comes to plasmons, because he was really one of the pioneers in figuring out a lot of the physics that happen and a lot of applications that happen. And so he wrote this book about this. And I think it's a very nice perspective. That's why I'm using this book for this topic quite a bit, just so you are aware is not just a random guy, but he was actually very heavily involved in this field when it came up and contributed a lot to this field. And so once you then once you actually go through this full procedure, and you can derive then the dispersion relation for surface plasmon polaritons propagating in x direction. And so of course you will again end up with a correlation between the wave vector and the frequency. And in this case, it looks like this. And what you in particular have to remember is actually how to draw this in a dispersion diagram. So again, if you're now looking at our full dispersion diagram of a metal, and what you can see now is that we're actually getting not only this branch here, which is shown in green, which should already be familiar with you for you, because that's what we have been talking about today in the first lecture. But in addition to that, we can get the second branch here, which is the dispersion relation of the surface plasmon polariton. And so a few features here are very interesting. So first of all, when we look at very small wave vectors, we can see how this dispersion relation is actually very similar, or like even or even the same as the vacuum dispersion relation. So for very short wave vectors, so very long wavelengths, we have the same as in vacuum. But then what will happen is that the curve becomes more flat and flat and flat. And in fact, at a certain point, it approaches here a horizontal. And so this horizontal is now given what we call by the omega SP, so it's the surface plasmon frequency, is this horizontal that we are approaching here. And we have a certain frequency regime between omega SP and omega P, where there is really no propagation in the metal allowed. But let's say before, for frequencies shorter than omega SP, smaller than omega SP, there is propagation allowed in the form of surface plasmon polaritons, so only on the surface of the metal. Then there is a window in which no propagation at all is possible in a metal. So that's here this gap between omega SP and omega P. And then there's propagation in a metal allowed again in the form of bulk plasmons moving through the metal. And so now I will also come back to the question I was asked earlier. What you can namely now see is that if we go to increasing wave vector k, our curve here, this purple curve that's showing the dispersion relation of the surface plasmon polariton, will get flatter and flatter and flatter. And it will actually approach the horizontal here. And so now if you think back about what this tells us, and that's really something, when you look at a dispersion relation, it should immediately click and be like, oh, there's a horizontal dispersion relation. And that tells us now something very important about the propagation properties of the light. And I would actually like to address the question to you. What does it mean if we get a horizontal dispersion relation? Can someone type it in the chat? What does it mean for the propagation of the light? Exactly. The group velocity is 0 or approaches 0. It gets very, very small. So for those who are not aware where this is coming from, well, a very flat curve means that the derivative will be 0, and the group velocity, so the velocity with which a group moves of waves moves through material, is given by the group velocity, which is given by the derivative of omega by k. And here in this regime, this derivative becomes 0, and therefore the group velocity becomes 0. So that means that we have something propagate at, or like this oscillation between free electrons and the electromagnetic wave. We have this propagate here on our surface, and the larger our wave vector gets, so the smaller our wavelength gets, the slower this is actually propagating. So it will have actually propagate like very, very slowly here on the surface, and therefore it will have a lot of time to interact in a certain position, and therefore it will also get absorbed quite fast. And so that's now answering the question that I received earlier, is no, it is not evanescent in x direction, it is propagating in x direction, but because it is propagating very slowly, there will be a lot of interactions, and also the absorption, therefore, will be quite high. Okay, and so now I'm answering the question that I then got afterwards, is the difference between vacuum and other dielectrics. So yes, there is a difference, namely whether or like which light line the surface plasmon is approaching. So far we always just talked about a random dielectric, so we didn't really specify what the slope here of this air, what the slope here of this light dispersion relation is. Yeah. So far we just assumed it's just a straight line that we, for example, get in vacuum. But in first order approximation, if we assume that we don't have any frequency dependence of the material, we would also get a straight curve in a different dielectric. The difference between air and dielectric with higher dielectric constant then being that this curve here will be a little less steep. So it will be more flat. It will have a the derivative here of this curve will be small. It will have a smaller group velocity. And so this would, for example, be the light line in air, and this would be, for example, the light line in silica. And now the difference between the surface plasmon polaritons that we get either in air or in silica is that in air we have now the here our surface plasmon will approach this air light line, whereas in silica it will approach this silica light line. So again, we have it can be the same metal, so it can be, for example, silver, and then either air or silica on top. And depending on whether it's air or silica on top, our dispersion relation will look slightly different, and we will have either here this branch that is close to the silica light line, or this branch here that's close to the air light line. That's actually quite important, namely because we also need to think about how can we couple in or how can we actually excite such surface plasmon polaritons. And if we only have a surface where, or if you have a situation where we have our metal in air, what we would get then is that we have here our dispersion relation for air, and here in blue, in black, and then here in blue we have our dispersion relation for the surface plasmon polariton. But there's no crossing point here, so there's no point where we can couple them in a constructive way, where they would not, where we can actually excite this surface plasmon polariton. So what we need to achieve is the situation where we actually can, on one hand, have our surface plasmon polariton here going in air, but on the other hand, we need to have some sort of interaction with light that is actually not in air, but in a different medium, for example, silica. And then we get here this red light line, and we get a coupling point here at which we can really couple light from air to our surface plasmon polariton. And so with the dispersion relation, we can understand why this is the case. And practically, we can achieve this through, for example, using a prism. So we can use a prism which we bring very close to the metal that we have here. And then what we do is we use light, and we shine in the light such that we get total internal reflection here in our prism. Then we have an evanescent wave that will propagate, or that can interact here with our surface plasmon polariton and excite the surface plasmon polariton. So the distance here between our prism and our metal has to be small enough so that this evanescent wave can couple into our surface plasmon polariton mode here that we create here on the surface. Alternatively, we can also use a prism and put a very thin layer on metal on top, and then we can actually get an excitation of the surface plasmon polariton here on the other side of the metal. So here it wouldn't be possible, because here at this interface, we would just be in a situation where our surface plasmon polariton doesn't look like the blue curve, but it would actually approach this red curve. And again, there wouldn't be a crossing point of the two dispersion relation. That's why in such a configuration, we can only excite a surface plasmon polariton if we then use a very thin metal layer, so that we still get some evanescent wave here at this metal air interface. And that's then how we can excite the surface plasmon polariton, traveling then here at this metal air interface. So that's how we can do it on one hand. The other way we can do it is by introducing some sort of texture. And if we introduce a texture, that's something that we kind of also thought of, or like talked about when talking about the imaging, then we are effectively introducing a periodicity, and therefore we are shifting the x component of our k vector, and we are shifting in such a way that the periodicity is now introducing this shift, where we can then find a position here, crossing point in our with our light line, with our now shifted light line due to the grating. and our surface plasmon polariton. And so these are the ways that we could excite surface plasmon polariton. Keep in mind that just coming from air without doing anything, it wouldn't be possible to couple into surface plasmon polariton. In reality, so that's now something from my own research experience. As you know, I work a lot with solar cells. You might think, well, where would this come up in solar cells? Solar cells do use, for example, metals for current extraction and a lot of dielectric layers in order to improve the optical performance. And in fact, there you can often observe plasmon absorption or unwanted excitation of plasmons, and thereby then unwanted absorption, due to the fact that just the surfaces are not perfectly smooth, but you always have a little bit of roughness, and that then gives you like surface plasmon excitation, although you didn't even design it for it. So it can even be an unwanted effect. So for me, most of the time, I actually don't want the surface plasmons, but other people do want them and can do really cool research with it. We'll talk about this in one of the next slides. But keep in mind that you can very controllably introduce some sort of grating, but just by having some sort of surface texture or roughness, often you end up coupling into surface plasmons, even if you don't design for. So just as a side note. And one thing that's also very interesting is that we can get localized surface plasmon resonances in metal nanoparticles. So this is now from your book, from the Fundamentals of Photonics book, page 330. You can really see if I have a metal nanoparticle, I can get such a situation where my plasmon is now not moving along a surface, but because I have like this round structure, I actually get like this resonant behavior where my electron gas here moves in a coordinated way or oscillates in a coordinated way, and then there's this electromagnetic wave around it. And this, of course, now, or let's say where the resonance frequency now lies in such a situation, of course, depends a lot on the size of this nanoparticle. And what people can do who synthesize such nanoparticles is they can design the size such that you can really get the full color spectrum. So you can really synthesize these nanoparticles, dissolve them in a solution, and then you can get really colorful effects. And depending and that really depends on whether the colors then come from the fact that certain resonances are particularly preferentially absorbed. And and by doing this, you can create really any desired color. And that has, of course, a lot of applications in science, but it also did have a lot of applications before people actually even knew what a plasmon is. So there are these like very interesting examples of art where here, this was actually from 4th century AD, and you can see these cups that were colored with nanoparticles, with gold nanoparticles. And if you look at it in reflected light, it looks green, and in transmitted light, it looks red, because you are here absorbing I have to think about it. You have to, if in transmitted light it looks red, that means that you're preferentially absorbing the green spectrum, and that's why it makes it look red when you look through it, but green when you reflect or when you shine light at it. And there are also these windows where the color effects were actually achieved with gold nanoparticles without them even understanding what a gold nanoparticle is. Transmitted, I'm getting a question here. Transmitted means putting a candle inside the cup, or does the cup transmit? Haha, no, it means putting a candle inside the cup, correct, yeah. Or maybe something less flammable in case you don't want to destroy your cup. But yes, putting a light source inside your cup is what transmitting means. Okay, no further question? All right, I already said, well, this is cool for art, but of course there are tons of scientific applications for plasmons as well, and you can also find things at the University of Twente if you're interested in that. As one example, I wanted to bring up surface plasmon resonance spectroscopy. And so this the surface plasmon and the surface plasmon resonance are extremely sensitive. So for example, if I have some sort of metal here, and my surface plasmon is now traveling at the surface here of the metal and the air. So this is my prism now. I'm shining in with a light source that is a little bit diverging, so I have a little bit of a broader spot here, and this is coupling in now my my plasmon, my surface plasmon wave. And if I get adsorbance on this surface, this will actually influence the properties of the plasmon now so much that you can see this as a so let's say depending on what is now on the surface, your resonance condition will happen at different angles of the light coming in. And what you can then do is you can use a detector, and you can now detect under which angle your light is being preferentially absorbed due to the fact, or you're preferentially getting a dark spot here on your detector due to the fact that you are coupling now into a plasmon or a surface plasmon wave. And this is really so sensitive that you can measure then, or like you can really detect single molecules and really very, very like little amounts of chemicals that absorb to the surface can be detected, because this is such a super sensitive method. Okay, so are there questions so far about this topic?